Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series BSc Applied Electronics, and the first subject we are dealing with today is Semiconductor Devices and Integrated Circuits. Let's start with the unit 1, the PN junction diode, and the contents we are going to come across in PN junction diode is introduction, PN junction diode, biasing, VI characteristics. Before starting this unit 1, we need to brush up some of the things about semiconductors. What are semiconductors? How we are going to deal with the semiconductors? What are the types in the semiconductors? Let's start with the definition of the semiconductors. Semiconductors are the devices those conductivity lies between the conductor and the insulator. This is how it looks like. The conduction band and the valence band will be apart, and there is a forbidden gap. It is very narrow compared to the insulator and inductor. As in case of conductor, there will be no gap, there will be no forbidden gap. It will be almost both the conduction band and valence band are merged together. So, the valence electron can easily go to the conduction band and we will get the free electrons for the current. So, when we come to the semiconductor, there will be a narrow forbidden gap. So, we need a voltage to send the electron from the valence band to the conduction band. As in case of insulation, there is a forbidden gap which is wider. There is no free electrons for the conduction. This is what's the difference between insulator, conductor and a semiconductor. And the example for semiconductors are silicon, germanium, arsenic. Semiconductors are of two types. One is intrinsic semiconductor and another one is extrinsic semiconductor. These types are classified based on the types of the impurities that we are going to add. Impurities in the sense we call as doping agent. For n-type semiconductor, for intrinsic semiconductors, we are called as a pure semiconductors, where we are not going to add any type of doping agents. That is why it is called as intrinsic or pure semiconductors. And whereas in the case of extrinsic, we are going to add an impurities like what we call as doping agent. The impurities that we are going to add is like pentavalent impurities or trivalent impurities. Based on the impurities, we are going to classify the extrinsic semiconductors in two types. That is, first one is n-type semiconductor and another one is p-type semiconductor. Let's start to know what do you mean by n-type. When a small amount of pentavalent impurity is added to a pure semiconductor, it is called as n-type semiconductor. As I said, we are going to add an impurity for the extrinsic semiconductor to make it as a n-type semiconductor. Here we are observing in the figure that these are the silicon atoms and which is having the electrons here. These are all the free electrons that are surrounding the silicon atom. If we add the impurity like arsenic atom, it is having a pentavalent electron, as I said. So, pentavalent means it has 5 free electrons. These 5 free electrons will combine with the 4 free electron of the silicon. Free electrons in the silicon will be having only 4. This will going to combine with the 4 electrons of the arsenic and remaining 1 will be left over. This free electron will be helpful for the conduction of electrons in the valence band. Typically, this and another example of the pentavalent is antimony, phosphorus are some of the example, and the doping agent which we are adding for the intrinsic for extrinsic semiconductor to make it as an N type is called as donor impurities, which will going to donate the free electrons for the silicon, and so that we can get the free electrons for the conduction. Next we move to p-type semiconductor. In a p-type semiconductor, a small amount of trivalent element is going to added. Let us look at into the figure how it shows. There are silicon atoms and there is a gallium. This is the impurity, the doping agent. Here it is a trivalent, it has only 3 free electrons which will going to combine with the 3 free electrons of the silicon, and the leftover one hole will be remaining. So this will make us a p-type semiconductor. Since there is only holes are left over here, so we call this as a p-type semiconductor. And the impurities that we are going to add here are example gallium, indium or boron. Such impurities which produces p-type semiconductor are known as acceptor impurities, because these are going to produce as a holes. So this type of impurities will produce an holes, and this type of semiconductor we call as p-type semiconductor. Next we move on to p-n junction. Now we come across the n-type and p-type. What will going to happen if we join this p and n type? Let's see. If we join these two semiconductor materials together, they behave in a very different way, merging together and producing what is generally known as p-n junction. So when we merge these two type of semiconductor, it will produce a junction, what we call as p-n junction. What happens when the n-type semiconductor and p-type semiconductor materials are first joined together? When we join first together, there will be conduction of negative charged acceptor ions. That is what in the n region. In the n regions, as we know, the electrons are the majority carriers, since the holes will be present, but it is of very less number. Electrons are the majority carrier in the n region, and in the p regions holes are the majority carrier. When we join the n and p region, there will be a diffusion takes place because of high potential gradient. The electrons are moving from the n region to the p region, and same ways in the p region the holes are the majority carrier. This will going to move from the p region to n regions and leaving behind the negative acceptor ion in the p region and the positive donor ion in the n region. This is what we call as a depletion layer. This will sustain till long when the enough energy is there for electrons to move from n region to p region. The depletion layer will grow on till the electrons will have sufficient energy to cross this from n region to p region. Okay, there will be a depletion layer will be created. This is called as potential barrier. Depletion layer has a for neutrality. How to maintain this neutrality? There is a density of electrons, positive donor ions electrons in the depletion layer, as well as a negative acceptor density in the depletion layer. These two will be of equal in density. The charge density of the p region and the n region will be of same. Suppose if there are positive donor of 6 number, there will be a negative acceptor ion of 6 number. Okay, this will create a neutrality. The formula will define like this: dPNA is equal to dN and D, that is negatively charged acceptor ions into the density of the p region, that is equal to multiplication of the density in the n region with the negatively acceptor ion in the p region. Next, what do you mean by the diode? Diode is a two-terminal device which will going to conduct in only in one direction. So how we are going to make a diode? Till now we discussed about the p-n junction, how it works, how the electrons will going to move, and how the depletion layer will form. Now we are going to make this p-n junction works as a diode. The effect of adding this additional energy source results in the free electrons being able to cross the depletion region from one side to the other. The behavior of the p-n junction with regards to the potential barrier's width produces an asymmetrical conducting two terminal device that is called as p-n junction. There will be asymmetrical conduction between the barriers, that is called as p-n junction diode. The p-n junction diode is one of the simplest semiconductor around and has the characteristics of passing current is only one side, and it has the, unlike a resistors, it is, and it is a VI characteristic is not linear because it is varying and it is exponential function of current. So, we can't apply the Ohm's law for this p-n junction characteristics. So, then the depletion layer widens with an increase in the application of reverse voltage and narrows with an increase in the application of a forward voltage, which we are going to deal in the next further slides, the forward and reverse two types of bias in the biasing topic. This is due to the difference in the electrical properties, that is mainly due to the application of impurities. So, one of the most common application of the diode is rectifier. It is used as a rectifier, and let us see what is the symbol of a junction diode. This is p type material, this is n type material, and this is a depletion region. As I said, it is conduct the current only in the one direction. This arrow mark indicates the direction of the current flows, and this is the anode terminal, this is the cathode terminal. This is schematic of a diode, and this is how it is looks physically. The strips marks on the diode will indicate the cathode. Next, we move on to a very interesting and important topic, biasing of diode. In biasing, what do you mean by biasing? Biasing means application of external potential voltage for the p-n junction diode. There are three types of biasing. One is zero bias, and another is forward bias, and another one is the last one is reverse bias. Let us start with the zero bias. The zero bias means, as the name says, there is no external voltage potential is applied to the p-n junction diode. In a reverse bias, what we do is we apply a negative voltage for the positive type of the p-n junction diode, and the negative region is connected to the positive terminal of the external voltage. That is what we call as a reverse bias. In a forward bias, what we connect means the n type p-n type of junction in n region is connected for the negative terminal of the external voltage, and the p region is connected to the positive terminal of the external voltage. This is how we are going to connect in the forward bias. In zero bias, how we are going to connect means we are not going to give any external voltage. So, we are shorting the terminals of the diode as shown in the figure. When a diode is connected in zero bias condition, no external potential energy is applied to the p-n junction. However, if the diode terminals are shorted together, a few holes in the p-type material with enough energy to overcome the potential barrier will move across the junction against this barrier potential. This is known as forward current. In a zero bias condition, we are not going to give any sort of external voltage. What will going to happen with the holes and electrons inside the p-n junction? Since we are not going to give any external voltage, there are some holes. There are some holes in the n regions and there are some holes in the p regions which have sufficient energy to cross the barrier. This minority carrier we call as minority carriers in n region because the electrons are the majority carriers. So, in n region the minority carrier will conduct from n region to p region. Similar way, the sum of the holes in the p region will conduct from p region to n region. From n region to p region, the conductions is called as producing a forward current, that is IF, and from p region to n region produces a current called reverse current, that is IR, which is in equal and opposite direction. So, the net flow of current we can say it as a 0, which is equal and opposite. So, we can say the net flow of current is 0. Let us take a short break and we will come back and we will continue the next topic. Welcome back after a short break. In the previous section we have discussed about biasing and we started about zero bias, and now we are going to continue the topic zero bias junction diode. We know that due to the we are not going to give any external voltage for the diode, there will be no current flow and there is a current due to the minority carriers, and that current will be 0 because it is flowing in the opposite direction, and this IR is called reverse bias and IF is called forward bias. When minority charge carriers are moving in the opposite direction, a net zero current flow in the circuit. The potential barrier opposes the migration of electrons and holes across the junction and allow the minority charge carriers to drift across the PN junction. As I said, because there is no external force, there is no conduction of electrons and only few current is flowing due to the minority charge carriers. This will going to deplete, this will going to suppress the conduction of electrons and holes due to the depletion layer present in between the PN junction. The minority carriers are constantly generated. In zero bias, only current is present due to the minority carriers. So, the minority carriers are usually generated by the thermal energy. If you are going to rise the temperature to create the minority carriers, there will be a sufficient large amount of current called as leakage current. Only the temperature is increased. So, we need to note down, whenever we say the leakage current is only due to the minority carriers. This current is no use because we are not at all connect the junction diode to any circuit. Since it is a leakage current, it is of no use. Next type of biasing is reverse biasing. We already discussed about reverse biasing, where we are going to connect the P type material to the N terminal of the external voltage, and N type material of a PN junction is connected to the P terminal of the external voltage. When a diode is connected reverse bias condition, a positive voltage is applied to the N type material and the negative voltage is applied to the P type material. This is how we are going to connect in the reverse bias. N region is connected to the P type of external voltage and the P region is connected to the N type of material, and this is the circuit diagram how we are going to represent for a reverse bias condition. This is anode, this is a cathode, that is, this is positive terminal connected to negative and the negative terminal is connected to positive. I is equal to 0, else there will be no current, and it is symbolically represent as a open circuit. Let us see what happens for a reverse bias. The positive terminal applied to the N type material attracts the electrons towards the positive electrode. Since the unlike poles attracts each other, so N type materials having the majority carrier electrons, this will going to attract by the positive terminal of the external voltage, and likewise the holes are the majority carrier in the P type. This positive holes are attracted towards the negative terminal of the external voltage, and thus the result is that the high potential barrier is created, thus the depletion layer width is increased, it becomes wider, so that we can expect there will be no possibility of any conduction. This condition represents a high resistance value to the PN junction and practically zero current flows. However, a very leakage current in the sense, as I said, only due to the minority charge carriers conduction. So, this will exist and it is of very low amount, we can measure up to a microamps. One final point, if the reverse bias voltage VR applied to the diode is increased to a sufficiently high enough value, it will cause the diode's PN junction to overheat and fail due to its become shorted. When we increase the VR, the negative reverse bias voltage, the reverse bias voltage is sufficiently increased, there will be a possibility of short fails of a depletion layer due to short of PN junction. If this junction is shorted, we can expect a very high current flowing in the junction, and thus it is called as a reverse bias current. This will be shown in a VI characteristics. Observe the graph where when the voltage, external voltage we given is sufficiently high, there will be increase in the current. This is called as a breakdown region, because due to the breakdown of the depletion region there will be a short circuit in the circuit and the current will flows. This is called as reverse bias current. Next we move on to forward bias. In the forward bias, the P type of the PN junction is connected to the positive terminal of the external voltage and the end region is connected to the negative terminal of the external voltage. Let us see what happens when we connect in the forward bias. If this external voltage becomes greater than the value of potential barrier, there will be a potential barrier in between PN junction and there will be a certain voltage, approximately 0.7 volts for silicon and 0.3 volts for germanium. The potential barriers opposition will be overcome and current will start to flow when we cross this 0.7 or 0.3 voltage for germanium. So, if we apply the voltage which exceeds the 0.7 voltage for silicon and 0.3 volts for germanium, we can expect the conduction. That is what it is saying. This is because the negative voltage will go into pushes the electrons. Here we are going to connect negative to negative terms. So, the electrons here, this is negative, this is also negative, it repels, it going to repulse the electrons. Here also the positive terminal is connected to P type. So, these two are repulse. Due to this repel action, the depletion layer become very small. Due to the depletion layer becomes very small, there will be a possibility of conduction of electrons which will going to cross the PN junction and the current will flows in the circuit. The application of forward biasing voltage on the PN junction diode results in a depletion layer becomes very thin and narrow, which represents a low impedance path in the circuit. This is due to the application of external negative voltage for the N region and the positive voltage for the P region. The point at which this sudden increase in current takes place is represented as a knee point, which will going to represent as a knee point as shown in the characteristics of forward diode. I also said there will be a voltage which after that only we can expect the conduction. For silicon it is 0.7. After this point there will be a increase in the current in the forward bias condition. So, this is called as forward bias region. This point we are called as a knee point. This condition represents the low resistance path through the PN junction, allowing very large currents to flow through the diode with only a small increase in bias voltage. So, for very small increase, for a very small increase we can expect a increase in current, very large increase in the current. This is what we expect for diode in a conduction mode. Since a diode can conduct infinite current above this knee point, as it effectively becomes a short circuit, therefore resistors are used in series with the diode to limit its current. In the schematic we can observe we are placed a resistor in front of a diode. In the conduction mode there will be a increase in the current, that is the diode will going to conduct infinite current. So, for limiting the current, a resistor is placed in front of the diode. Next we are moving on to the VI characteristics of junction. What we are read in zero bias, forward bias and reverse bias all are drawn in a graph called VI characteristics. In forward bias we know that only above the knee point we can expect the conduction as shown in the graph. This is a knee point and 0.7 volt for silicon, 0.3 volts for germanium. After this voltage only the electrons will going to conduct, we can expect the current flow, and this condition is called as forward bias condition, and this region is called forward bias region. And in this condition there will be high current flow and the diode is in forward condition and also it is shorted. In the reverse bias condition there will be a low current and there will be a sudden increase in the current when there is a reverse breakdown voltage which will going to break down the depletion layer, and there it will be shorted, there will be sudden increase in the current. This point is called as a Zener breakdown or avalanche voltage or Zener breakdown voltage. This is called as reverse bias region. These are the characteristics that we can observe from the VI characteristics of a diode. The junction diode ideal and real characteristics. In ideal conditions, what is the condition means, when we are going to vary the voltage, the current remains same, and but it is not practically true. But in the real condition, what is happens means, when we are going to vary the voltage, the current varies according to the voltage. That is shown here with the symbols and the graph. This is what for the ideal junction diode, and this is the characteristics for the real diode. This is a symbol, it is both same. For the real diode, we are going to give the external voltage in forward bias condition and in the reverse bias condition also. For ideal, it is not the case. Next is a summary. What we are come across in this session is semiconductor definition, the two types of the semiconductor, and which is a majority charge carriers in the N type, majority charge carriers in the P type. About the doping agents we come across for P type and N type, and also we come across a depletion layer because of the forward bias and reverse bias and zero bias, what happens for the thickness of the depletion layer. And also we come across the approximate voltage for forward bias in silicon and germanium, and we also come across the leakage current. Some of the questions of this session we can expect is, what is biasing, what is PN junction diode, explain the three types of biasing in PN junction diodes. The references are electronics tutorial, electronics hub, and electronic devices and circuits for JK Mittal, GK Mittal and Khanna publishers. This ends up the PN junction unit 1 lecture 1. Thank you.